So we don't have the license plate of that one because we didn't really have the cameras, the automatic cameras were running. Of course, there wasn't any law to back that up at that time. So we don't have the license plate of that Apollo asteroid, but it was definitely Apollo asteroid that caused the extinction of the dinosaurs. All right, so anyway, Apollo and Amor, two classes of asteroids. You should understand what the distinction is there for the final, because all the material we're covering now is going to be on the final as well as material from the first three exams. All right, so moving ahead with the Lagrange points. All right, so I talked about how there's 5 Lagrange points, but I mentioned that the Trojan asteroids are only at L4 and L5. That's where we saw that little bunching on that photo I showed you, right? That diagram. We don't see bunches of asteroids at L1, L2, or L3. So now I'm going to talk a little bit about why we get the bunching of Trojan asteroids at L4 and L5, but not at the other points. I mentioned that they're all equilibrium points, so they all represent points in space where the forces balance, okay? But there's another consideration on top of that, which is the stability of the situation. So you can have equilibrium at L1 and L2 and L3. That means if you could be God for a moment and you could put an asteroid at L1, L2, or L3, it would be in equilibrium. But suppose now that it gets displaced just slightly. Maybe another asteroid goes by and its gravitational force displaces this asteroid that you just placed. You put it there at L1, L2, or L3, but now it got perturbed by the gravity of another asteroid or something. Okay, so then we get to stability. The question is, what happens if you gently nudge an asteroid at one of those 3 points? Well, these 3 points are unstable. All right, so what that means is if we start off with an asteroid right there at L3, and then we nudge it a little bit, it'll move away. It'll move away from L3. So L3, and likewise L2 and L3, L1 and L2, are not points where asteroids will accumulate. You see, because if there's one sitting there and it gets perturbed, it'll move away. So those are not points where you'll get an accumulation of asteroids. So these little wiggly things indicate that we have motion away from those points. Now when we look at L4 and L5, it's exactly the opposite situation. Those are stable points. If we take an asteroid sitting at L4 or L5 and we gently nudge it a little bit, it'll float back. Okay? So it's an equilibrium point, but it's a stable equilibrium because you get a restoring force, a gentle restoring force that will shepherd those asteroids back to L4 or L5. Completely different from L1, L2, and L3, which are unstable. Okay? So that's why we see the Trojan asteroids at L4 and L5, is because of that stability idea of having a force that actually shepherds the asteroids back to those locations. So now we understand how the Trojan asteroid populations actually form. Because as I mentioned before, you could have asteroids that drift into this zone beyond 3.5 astronomical units. Well, what's going to happen to them? They're actually going to get gently shepherded into these stable points, L4 and L5. So the Trojan asteroids represent this gentle accumulation over billions of years into those stable zones. All right, so we have stability. I mentioned already that there's a precise angle involved. Well, it's not exactly precise because you saw that the groups are kind of broad there. But anyway, the center of each of these groups is 60 degrees either ahead of or behind Jupiter's orbit. So again, if we go back to the diagram here, it means that these asteroids are orbiting at the same period that Jupiter's orbiting, around 10 years or something like that. They're orbiting ahead of Jupiter. You see that little arrow there showing Jupiter's orbit? And there's a group that are following Jupiter. But all these guys out here are orbiting with that same orbital period, which is the orbital period of Jupiter. We call these Lagrange points because Lagrange was a mathematical physicist who first deduced the existence of such points. He also played a role in some of the other orbital stuff that we've been talking about. All right, so a little more about asteroids. We've talked about the fact that they're relatively primordial. Well, there's degrees of primordiality, if that's a word. Somebody can Google me on that, but not now. Primordiality. I don't know if that's really a word, but go with it anyway. Okay, so we have these classes of composition, carbon-rich or silicon-rich. We actually went over this a little bit earlier in the semester. The carbon-rich ones are actually, for the most part, a little farther out in the solar system, and we get the stony asteroids a little closer to Earth. So even though the carbon-rich asteroids are pretty common, we don't get too many of them in the inner solar system because of this concept of solar system-wide differentiation, which I keep pounding into your head. I'm trying to think of a different way of putting that, but not much else I can say about that. Remember, the concept of solar system-wide differentiation means that the dense material, the iron, the heavy material is relatively close to the sun, and lighter weight materials are farther away. So we have iron-type meteorites are closer to the sun, carbon-type meteorites are a little farther away. Silicon asteroids are basically stony asteroids that are very similar in composition to the surface layers of the moon, for instance. All right, so here we have Matilda, 25 kilometers across, pretty average meteorite. It's had a difficult history. It actually lived in it was in a shelter for battered meteorites. We can talk about that now. We're starting past that. And we can see that meteorites do get highly cratered. You see, I mean, we're talking about little craters, and then we're talking about whomping, gigantic impacts. So this is, evidence for the kinds of huge impacts that can happen, even to unlikely things like asteroids. Asteroids are not very large targets out there. It's a big solar system. But amazingly, over the span of billions of years, so many things can happen that are very unlikely because you just have this huge expanse of time. So something as incredibly unlikely as a bullseye on little Matilda there, only 25 kilometers across, that's like 15 miles. That's like the size of the Beltway, roughly, right? So this is like the DC Beltway we're talking about. Can get whomped by huge impacts. This has absolutely nothing to do with it. Do you remember who this is? The name? Thank you. Cheddar. I like this photo. Relaxing. That's one of my favorite places. Relax. And this, I didn't know why I put this in, but now I understand. I understand that. Because remember I talked about that comet with the wispy tail? It's a lot like this tail, although it's not really in the right shape right there. Comets don't usually have hook-shaped tails. But yeah, we have 5 cats, and this is them all eating lunch together. And this is where you don't want to be that upper corner if they want to, because that's where they're all pointing at. You have to think that's cheddar. Okay, thank you. Thank you. All right, that photo on the left there you probably recognize because I already showed that earlier today. That's Vesta. That's one of those 4 huge asteroids that's in the solar system. By the way, it turns out not to be an Apollo asteroid, fortunately, because otherwise that would be a really dangerous thing to have running around. But you see that we don't have a very good photo again of that object. We've actually learned a little bit about Vesta in a very indirect way, because there are many examples of meteorites that have passed through Earth's atmosphere and landed on the ground. We can study them, and many meteorites, at least there's a class of meteorites found on Earth that have a chemical composition that matches the chemical composition of Vesta. Now you might think, how do we know what the chemical composition of Vesta is? We can't even get a clear photo of it there, right? I mean, that's not even clear enough to Photoshop and put Elvis on it or something. That's really a pretty fuzzy photo. But the thing is, we can do spectroscopic observations of the radiation coming off Vesta without being able to take a clear photo. You don't have to be able to take a clear photo. You just have to be able to collect all that light, pass it through a spectrograph, look for absorption lines, and when you see absorption lines, you can tell what that body's made of without even having the ability to take a clear photo. So we know from spectroscopic observations of Vesta that it's rich in a material which represents reprocessing on Earth, geological reprocessing, and we call that pyroxene. It's very common in lava flows on Earth, so it's related with metamorphosis and reprocessing, high pressures and temperatures. That's the same material that we see in some of these asteroids that have landed on Earth, not asteroids, but meteorites. So we believe that they are actually chips off the old Vesta, these objects that we're talking about. So we've actually, ironically, been able to learn about Vesta by studying meteorites, which are actually chips off of it, which we know because of this comparison between chemical analysis of the meteorites and spectroscopic observations of Vesta. So this is an example of a fragment. This is only a few inches across. All right, so asteroid Vesta, again, the best photos we have are Hubble Space Telescope photos. And actually, the reason we don't have really good photos of a major asteroid like this is because it's not an Apollo asteroid. It actually doesn't really get that close to Earth, so you've got to go way out of your way to actually take photos of this. And there's never been enough of a reason to actually send a space mission to where this guy lives and spend most of his time. So we rely on longer distance photography using Hubble, and the raw Hubble image is pretty spotty looking up there in the left-hand corner. But if we do computer modeling, we think the surface looks something like the upper right image, pretty weird shaped with a mottled surface, probably again due to radiation darkening because of billions of years floating around in space. All right, so let's talk a little bit more about the Apollo asteroids. I already mentioned the Apollo asteroids are the class of asteroids